So today we're going to be starting Chapter 4, Section 1. Which is about inverse trig functions. So hopefully you guys remember a little bit back to your algebra class from last year about inverse functions in general. So let's just think about the function y equals sine x to start with. So the graph for that function looks like this, right? We remember that? Now, if you remember back from your algebra class last year when we found an inverse for a function, how did we do that? Jason? Great. So the key part is we swap the x and y variables, and then we rearrange to get the y by itself again, right? So if we just swap the variables, what's going to happen to our graph? Is we end up getting something that looks like this. What's the problem with that? It's not a function. Great. Why is that not a function? Great. It fails a vertical line test. We can draw a vertical line that intersects this function in more than one place. Does everybody kind of remember that? And this could happen occasionally when finding inverses, right? Does anybody remember what we can, or how we could look at the function y equals sine x and immediately tell that there's going to be a problem with its inverse? Great. So there's a horizontal line test. You might have remembered from your algebra class last year that if a function fails a horizontal line test, its inverse will not be a function, right? The failing of a horizontal line test implies that the function is not one-to-one. That's the mathematical term that we really need to make sure, or need to have in order to make sure our inverse will be a function. Do you guys remember last year in our algebra class what we did to fix this problem? How did we take a function and do something to it so that its inverse would also be a function? Teresa? Yeah, so what we do is we restrict the domain. That's exactly the right idea. So with the graph here of sine of x, the domain is negative infinity to positive infinity, and the range is -1 to +1. The problem here is on our inverse, the domain is -1 to +1, and the range is all real numbers. So what we need to do is we need to somehow restrict our domain so that the range remains the same, but we don't have any duplicating y values, y coordinates. So what we do is we take just like that part of our function. So we're going to limit our domain to just between, or just that part of our function. Notice that we still get the entire range by doing that. Our function still goes from -1 to +1 on the y-coordinate. But we don't have any duplicating y values by just taking that small section of the function. So when we do that, our graph will look like this. And our domain is now -π/2 to +π/2. And our range is still -1 to +1. So when we do that, then our new inverse there now looks like this.
Excuse this interruption. Would the following students please come to the Media Center for pictures? Nicholas Clem, Nolan Tompkins, Tanner Borgio, Kyla Jackson, Megan Tompkins. Please come to the Media Center at this time for pictures. And if there are any seniors who would like their pictures taken, please come to the Media Center at this time.
Now, this is a function, right? So we're going to give this function a name. We call this function the sine inverse of x. So when we talk about sine inverse, remember that sine what we do is we take an angle measure and we map it to the y-coordinate on a unit circle. So sine inverse is going to take a y-coordinate on a unit circle and map it back to some angle measure. Just to kind of reiterate the relationship between these two things. We spent a little bit of time there thinking about sine graphically to kind of justify how we need to restrict the domain in order to create an inverse function. But let's talk again what this relationship is between sine and sine inverse, because that's an important thing to kind of keep in mind. Okay. Is everybody okay with this notion? Okay. Okay. So what we've done here is all concerning sine specifically, right? But we could do a similar thing for cosine and for tangent as well. Let's just summarize the result. Is that okay? Oops. Oops. Those are in the wrong places. My apologies. Hopefully I got there before you did. Okay. So the big takeaway, the piece that is going to be really critically important that you guys are responsible for remembering, is the range associated with each one of these inverse functions. That's the piece that's going to be necessary to remember for like a test or quiz or homework kind of setting. So let's run through some examples of kind of how we would go about using these to do some homework problems. Right? So let's do some examples now of how we can use these. Do I need to give a minute? I see a lot of people still writing. Slow down. It's okay. You can tell me like, hey, I'm still writing before I start going on and doing something different. We have lots of time. You know? Is everybody okay with kind of how we built out these inverse functions and what we did here? So the beginning part was not something we would ever really need to reproduce in a homework assignment, just kind of explaining to you what these inverse functions are and how we made them work and why their ranges are specifically what they are. Because without talking about why that is, it doesn't make a lot of sense as to how we got these specific ranges for the inverses. But that part is really important that we're able to remember that. So I wanted to kind of explain where they come from before we just presented you with those ranges and be like, okay, these are what you need to remember. You know? All right. So let's look at an example. So let's say we wanted to find the exact value of sine inverse of -1/2 without using our calculator. Is everybody okay with that? So sine inverse of -1/2 is equivalent to asking, is going to be looking for an angle measure, right? It's basically the same thing as saying, okay, sine of what angle gives us the output of -1/2. That's just kind of using our definition of inverses from Algebra 3-4. It's an equivalent way of thinking about the same question. This might be a little bit more natural for you guys to think about, so I'm just kind of presenting it in that way. Is that okay with everybody? Now, sine is negative in what quadrants? Good. Should be quadrants 3 and quadrant 4. Because the sine is the y-coordinate on the unit circle. The y-coordinate is negative, but when it's below the x-axis. So we're saying it's like that part of the unit circle, right? Now, if I go over here and I think about sine inverse has a range from -π/2 to +π/2. What quadrants is that? Well, 0 to π/2 is this part, right? And 0 to -π/2 is that part. So here we're in quadrants 1 or quadrant 4. Where should our answer actually be located? Quadrant 4, because it's true in both of these places. Is that everybody okay with that? So to find that angle theta now, I'm going to go to my unit circle. And I'm going to look in quadrant 4. So looking down here in quadrant 4 for the location where the y-coordinate is -1/2. And I'm going to figure out the angle for that, which is 11π/6. Is everybody okay with what I did there? Okay. Now, this is not our actual answer, unfortunately. What's wrong with this answer? It's not, oops, should be a bracket, in the range for sine inverse, right? The output for sine inverse needs to be between -π/2 and +π/2. 11π/6 is definitely bigger than π/2, right? So what do we need to do to this answer to make it correct? We're just going to find an angle that's coterminal to 11π/6 that does lie inside of that interval.
Excuse this interruption. Would any juniors who want pictures retaken, any juniors, please come to the media center?
And how do we find an angle that's coterminal again? We add or subtract 2π in this case, since our angle is in radians. Since our angle is too big, we'll subtract. And we get -π/6. And that is in our output or the range for sine inverse. So that is our answer. So to reiterate kind of what we did here, let's just kind of go back and summarize, because we did a lot of things here. Although I wrote a lot of stuff down, most of this is things you could do in your head. Okay. So I started by figuring out what quadrant sine was negative in and what quadrant sine inverse an answer from sine inverse should lie in. There always will only be one result in there. It'll always be one quadrant or the other. It will never be both. It'll never be neither. Okay? I then went to the unit circle to find that angle that met that criteria. And then I checked to make sure the angle lay in the range for the inverse function. And if it didn't, like it did here, I just found something coterminal to it. Victoria.
Can you explain why you found quadrant 1 and 4 again?
So for sine inverse, the range is always negative pi over 2 to positive pi over 2. So 0 to pi over 2 is quadrant 1. And 0 to negative pi over 2 is quadrant 4. Is that okay?
Yes.
Okay. Josh, you had your hand up?
Yeah, I heard the same question.
Did I answer it for you also? Okay. What part did I lose you on?
I was just trying to know that. So, in this way, how come it's 0, 5, 2?
So sine inverse has a range that goes from negative pi over 2 to positive pi over 2. Okay with that? That's what we started off by doing, figuring that out. Now that's always going to be the case for sine inverse. That part will never change. So the angles between 0 and pi over 2 is just the stuff in quadrant 1. That's stuff between 0 degrees and 90 degrees. Right? The stuff between negative pi over 2 and 0 is like quadrant 4. That's the stuff between negative 90 degrees and 0. Remember, negative is we're going clockwise instead of counterclockwise.
Yeah.
So that's quadrant 4.
Okay.
Does that feel okay?
Yeah.
Okay. All right. Let's do another one of these. Sound good? Oh, actually, before we do another one, let's present another way that we could do this without using the unit circle. Okay? So I'm going to pick up at this spot. So we've identified our answers in quadrant 4, but instead of going to our unit circle, I'm going to do something different. And it doesn't matter to me which one you do, but I want to present both options for you, and you can do whichever kind of feels more comfortable. So we know our answer is here in quadrant 4. So there's our angle. Everybody's okay with that? Since I know that sine is equal to negative 1/2, I know that this side is, the hypotenuse is 2, and the opposite side is negative 1. Right? or you could think about it as y over r, if you prefer that definition. We talked about how those are really kind of equivalent. So far, so good? I can use the Pythagorean Theorem then to figure out that third side. And what I notice is that this is a 30, 60, 90 triangle. Everybody okay there? How did I recognize it was 30, 60, 90? By the side lengths, right? Because the side lengths were 1, square root 3, and 2. That tells me immediately that it's a 30, 60, 90 triangle. And specifically that angle there is 30 degrees. Is everybody okay with that? So, if I am talking about the angle of rotation, here, that's negative 30 degrees. Or when I convert it into radians, negative pi over 6. Is that okay? So the advantage here is I didn't have to really find anything coterminal. I was able to go immediately into my negative pi over 6 answer without having to find a coterminal angle, which is fine. Or you could do it the other way. Either is fine. Okay, they both work. Let's do another. Yes? Okay. So let's say we want to evaluate cosine inverse of square root 3 over 2. So I know that this is equivalent to this statement. Here I know cosine is positive in what quadrants? 1 and 4, where the x-coordinate is positive, because remember cosine is the x-coordinate on our unit circle. Now my range for cosine inverse is from 0 to pi. So that's quadrant 1 and 2. Right? Because pi is really 180 degrees. So that's 0 to 180 is quadrants 1 and 2. Everybody's okay with that? And now we could either look up our value from the unit circle or we could draw a picture. Let's use the unit circle again. I think that's the easier route. So the answer I'm looking for is going to lie in quadrant 1. And it's going to be the location on my unit circle in quadrant 1 where the x-coordinate equals square root 3 over 2. So I'll go to my unit circle, and I'll look in quadrant 1, I'm going to find where the x-coordinate is square root 3 over 2. And that x-coordinate is the one that I need. Or I'm sorry, that angle measure is the one that I need. Is everybody okay with that? Okay. And I noticed that pi over 6 is in the interval for cosine inverse, or is in the range for cosine inverse. So that is my answer. No need to find anything coterminal. Is everybody okay there? What do you guys think? Do we got it okay? Again, yes, Gracie. Sure. So let's say we'll do tan inverse of -1. So again, we'll start by writing out our equivalent statements. So I know that for tangent inverse, the range is from -pi/2 to +pi/2. So that's quadrant 1 and quadrant 4. And tangent is negative in quadrants 2 and quadrant 4. So I'm going to go to the unit circle in quadrant 4, where y over x is equal to -1. Everybody okay with that? Tracy, are you good so far? Okay, so let's go look at our unit circle. So I'm looking in quadrant 4. And I notice here, if I take the y coordinate, divide by the x, I get -1, right? Because they're both the same value aside from the sine. So that angle is 7 pi over 4. Is everybody okay there? Now, the last thing I need to do before I take this as my answer is to make sure that this is in the range for tangent inverse. Unfortunately, it's not, right? It's too big. 7 over 4 is definitely bigger than 1/2. So how do we fix that? We just find an angle coterminal to it. Since it's too big, we'll be subtracting 2 pi. Which gives us -pi over 4. And that is in our interval. So there's my answer. Excuse me. Does that feel okay?
Sorry for the interruption, but it
this time, any sophomores that need to have their picture retaken, please come to the media center.
Oops. What if we wanted to do this? Cosine inverse of tangent of 45. Well, this looks pretty terrible, but it's not bad. It's really the same problem as what we had before. It just includes one extra step. So on this problem, we'd want to start with the inside, because tangent of 45 is just a number, right? We can find that number by going to the unit circle, locating the 45-degree angle, and then remembering that tangent is y over x. So this is going to be root 2 over 2 divided by root 2 over 2, which is 1. So we can say cosine inverse of tangent of 45 is really just cosine inverse of 1. Now it's just like the previous problems, right? So we just had one additional step in the beginning where we had to evaluate the inside part. But that's not so bad. So if I do that, I'll write down my two equivalent statements. So here, cosine inverse is either in quadrant 1 or quadrant 2. Cosine is positive in either quadrant 1 or quadrant 4. So here we want, looking in quadrant 1, so we're going to go to the unit circle, look in quadrant 1, and look for the place where the x-coordinate is equal to 1. That's happening right here, which is the angle 0. Is everybody okay with that? And I notice that this is in my range for cosine, so I don't have to do anything to that. It's my final answer. Is that okay? All right, good. So here I'm using an old notation. Arctan is the same thing as tangent inverse. Arcsine is the same as sine inverse. Arccosine is the same as cosine inverse. Just as a little heads up, they're just older notations. They're not used as commonly as before, but they're still used on occasion. So if you see that, don't be confused. It just means the same thing. Don't ask me why we have more than one notation for the same thing in mathematics. Why do you have, how many words do we have to say good in English? You never complain about that, do you? No. It's like, how come I have to say, remember good and excellent? You know, like nobody argues about that. It's the same thing here. All right, we have two symbols that do the same thing. No big deal. Is everybody okay with that? All right. So we'll approach this problem the same way we did before. So we're going to start with the inside. So I'm going to go to the unit circle and figure out what the value for tangent of 2 pi over 3 is. So 2 pi over 3 is here. So I have y over x. So that's negative root 3. Is everybody okay with that? So arctan of tangent of 2 pi over 3 is really just arctan of negative root 3. So write down our two situations. Here we have this one. So again, arctan or tangent inverse is in either quadrant 1 or quadrant 4. Tangent is negative in either quadrant 2 or quadrant 4. So what we need is quadrant 4. Going to the unit circle in quadrant 4, where y over x is negative square root 3. Everybody good with that? Oh, I wrote r there. That's supposed to be an x. I think I said x. Okay. So I'll go to my unit circle. I'm in quadrant 4. So y over x has to give square root of 3. That's this one, right? Where the y coordinate is negative square root 3 and the x coordinate is 1. You can ignore the denominator since they're both the same. They'll cancel out when we divide anyways. Is that okay? So the angle measure that I need then is 5 pi over 3. What's the problem with that though? It's not in the range for tangent inverse. So we'll just find an angle coterminal to it. And there's my answer. I want to point out here something. So usually, if we did f inverse of f of x, we'd expect to get x back, right? Notice that tangent inverse of tangent of 2 pi over 3 gave us negative pi over 3. That's a little strange. It's okay, because these are periodic functions. They're going to have the same value in these locations. Notice that this is a quadrant 2 and this is quadrant 4. In both of those locations, tangent is negative square root 3. But the range for tangent inverse is specific, so we can't ever get a quadrant 2 angle.
With the last name beginning with the letter A through M, as in Mary, may come to the media center for picture retakes. A through M come to the media center.
Is everybody okay there? So I just felt like I needed to point that out because that's a common thing that, or mistake I see students make, is they just like, oh, they just cancel out and I left with this angle. It's like, oh, no, no, no. You got to be careful. You can't get any angle to come out of these inverse functions. It can only be something from its range. Do we see that? Okay. You guys are doing well so far. What if we asked you to do sine inverse of negative 3.2? Or I'm sorry, negative 0.32. Can we use the unit circle to get this? Is negative 0.32 a y-coordinate on the unit circle? No way, Jose. What do we do instead? Well, how did we do sine of like 37 degrees? That's not a unit circle angle. Didn't you just use your calculator? What do you think we're going to do in this case? We're just going to use our calculator. So we'll type in sine inverse of negative 0.32. Now when we do this, we have to be a little bit careful. What mode does your calculator need to be in? It needs to be in radians, because notice that there is, well, I guess I don't have it in the directions. You could have had it in degrees and give a degree answer. I guess it wouldn't have been wrong. But this is an unfortunate example by choice in my part. Just look at what the answer is. It's almost the exact same as the input. That's not usually what happens. Just kind of keep that in mind. That's just an unfortunate coincidence in this instance. Is that okay with you guys? Remember, when you're doing sine, cosine, or tangent, if you're using those operations on your calculator, the mode matters. If you're just doing like addition, subtraction of stuff, like that's fine. But if you do sine, cosine, or tangent on your calculator, you got to be careful about your mode. What if we instead had asked to do cosecant inverse of 2.5? Is there a cosecant inverse button on our calculator to take advantage of? No. But we know, hopefully we remember, cosecant was related to one of our other trig functions in some way, right? Which trig function was it related to? It was related to sine. How is it related to sine? It was a reciprocal. So I can take that then and say that's the same thing then as sine inverse of 1 over 2.5. And that's what I'm going to type into my calculator, which gives me about 0.412. Is everybody okay with the algebra steps I did there to kind of work that out to give me something I could type into my calculator? Elizabeth? Of course. One last example and then we'll be done here for today. So, we're asked to find an algebraic expression for sine of arc cosine of 2x So this is similar to a problem we've already done, the difference being here that we have not a number. We're going to end up with variable expressions, but that's okay. So I'm going to start with the inside part. So if arc cosine, or theta is equal to arc cosine of 2x, that tells me that theta is equal to, or cosine of theta is equal to 2x. And I remember that cosine is adjacent over hypotenuse. So I'm going to have a right triangle with angle theta, where the adjacent side is 2x, and the hypotenuse is 1. I can then use the Pythagorean Theorem to find the other side. So I know that 1 squared is equal to 2x squared plus y squared. And 2x squared is 4x squared. And when I subtract that from both sides, I get that y squared is equal to 1 minus 4x squared. So y is just the square root of 1 minus 4x squared. The last thing I need to do is to determine whether that should be a positive square root or a negative square root. To do that, I remember that cosine inverse is either in quadrant 1 or quadrant 2. In both cases, in quadrant 1 or quadrant 2, the y-coordinate is positive. So that should be a positive. So now, if I wanted to do sine of theta, that's opposite over hypotenuse, which in this case is positive 1 minus, positive square root of 1 minus 4x squared over 1, or just square root minus, or square root of 1 minus 4x squared. So for your assignment here, you guys should be able to do 1 through 18 in the homework set. Next time we meet, we'll spend some time in class doing some more practice on this topic, doing some of these worksheets. You'll notice I put a bunch of worksheets also into PowerSchool into OneNote in the content library. You're not responsible for any of those yet. Nothing's been assigned, but we'll do some of them in class next time. This is an important chapter, though. We're tying together a lot of ideas from the previous chapters. You'll have noticed, right, and this is pretty common at this point now in this trig course, as we start circling back, and these things that we've learned before are coming back and becoming important again. So in a way, things start can either get easier if you learn the things well the first time, or it can seem to get harder if you didn't really learn the things well the first time, because there's going to be things you have to go back and relearn and that sort of thing. But be patient. Try to go slow. Think about what it is you're doing and why things are the way they are. If you have questions, feel free to ask. But you guys can do it. Okay? Well, that's it for today.